So we're going to spend a little bit of time talking about what we call pressure volume work and what is PV work or pressure volume work. Most chemical reactions, well, I mean, I won't say most, I guess most done in a teaching experience, a teaching setting, but a lot of reactions in general are done in open containers under constant pressure conditions. What I mean by constant pressure is constant barometric pressure, the atmospheric pressure around you. If I do this in an open container, it's not enclosed, then, and I don't just mean a lid, I mean like sealed off from atmospheric pressure, controlled pressure. Just open container, it's going to have the pressure of whatever else is around, every other piece around in the same atmosphere that it is in. We call this work pressure volume work or PV work. Now a little bit of background definition. Work is defined as our force applied over a distance. How much force was applied per distance. We defined pressure in the last module as force over area. So again, remember we talked about our force being applied over a specific area? What is the force applied here over this area that it's hitting? I can rearrange my pressure equation to say force is equal to pressure times area. So rearrange this into this. Now I'm going to substitute in P times A, pressure times area, for F in my work equation. So work, which is equal to force times distance, is going to be equal to pressure times area times distance. If I have a cylindrical piston just means cylindrical system, the piston can go up and down. The system can push down on the system can push up on the piston. I know work is equal to force times distance, but I've just shown you how work can be equal to pressure times area times distance. In a cylindrical piston, the distance here would be your change in height, delta H. So work is equal to pressure times area times change in height. If we add volume of the cylindrical piston, the volume would be your area times your height. So change in volume is equal to area times change in height. Now that I know my volume, I can substitute this in. I know that my work will be equal to negative P delta V. How? Well, I know my volume is area over height. I know my work is pressure times area times height. This is equal to my volume. So work is equal to negative P delta V. First law tells me delta E is Q plus W, heat plus work. I now can substitute this in for here. Now why is P negative? That's considering the system of the cylinder moving. The cylinder is doing the work. If the cylinder is pushing, the cylinder is doing the work, right? What do we know about work? If the system is doing the work, it's going to be negative. We can also do this so we can have reactions under constant pressure conditions or constant volume conditions. I want to clarify, if we are under constant volume conditions, W is still equal to negative P delta V, but at that point, W will be equal to 0. Why? Because they're in constant volume conditions, the change in volume is equal to 0, therefore, W has to be equal to 0 as well. In this case, delta E is equal to Q sub V. Sub V means constant volume. And so Q sub V, heat flow under constant volume conditions. We see in another module, we're going to see Q sub P, that means constant pressure conditions. Q sub V means constant volume conditions. If we are not allowing the volume of the system to change, we are under constant volume conditions, and work is going to be equal to 0. What is an example of a constant volume calorimeter? A bomb calorimeter. If I am letting a reaction happen, but I'm not allowing the volume of the system to change, I am producing a bomb. It is a common technique that we have. Our students that are in PChem do this experiment. We don't do it in the freshman level, but it is a common thing that we can do, and we're going to do calculations with bomb calorimeters in the calculations that we have. It's a slightly different calculation, but overall very similar to what we're going to do for the calculations under constant pressure conditions as well. Very useful conversion here, by the way, is 101.3 joules is equal to 1 liter atmosphere. We're going to be using this in some of the calculations we're going to do in this module. But also, if you ever wondered why the gas constant R is 0.08206 liter atmosphere per mole K, or 8.314 joules per mole K, you now have the conversion factor to go between the two. So let's look at a couple examples really quick on how we can actually apply this. The volume of an ideal gas is decreased from 9.75 liters to 1 liter at a constant pressure of 1.50 atmospheres. What is the work associated with this process? I know work is negative P delta V. I know my V1 was 9.75. I know my V2 is 1 liter. I know my P is 1.5. Negative 1.50 atmospheres. Remember, delta is always final minus initial. So V2 minus V1, or 1.00 liters minus 9.75 liters. Now, if I do this calculation right here, this is going to get me units of atmosphere liters, which doesn't make any sense for work. I need to remember my conversion factor. 101.3 joules to 1 atmosphere. Calculate this through, I get work equal to 1329 joules, and I'm going to round for sig figs. Now when I subtract here, I'm going to keep it to 2 decimal places, which is 3 sig figs. So overall I need 3 sig figs in my calculation, 1.33 joules. And so the work done here was 1.33 joules. And one more example. A certain reaction performed at 1 atmosphere of pressure gives off 6.20 kilojoules of heat. Gives off means it's negative. Q is negative. During the reaction, the volume expands from 1 liter to 44.2 liters. What is delta E for this reaction? Well, I know that delta E is equal to Q plus W. I know that W is equal to negative P delta V. Therefore, delta E is equal to Q minus P delta V. I've just told you that Q is negative because I'm giving off heat. Now, my conversion I'm going to use is 101.3 joules per liter atmosphere. This is in kilojoules. I'm going to go ahead and just convert that to joules, so I don't have to mess with it later. 6,200 joules of heat given off minus P delta V. My pressure is 1 atmosphere. V2, 44.2 liters. V1, 1.00 liters. And my conversion factor, 101.3 joules to 1 liter atmosphere. Delta E gives me negative 10576 joules. Check my sig figs. 1 decimal place here. When I subtract, that's still 43.2. So still 3 sig figs. 3 sig figs on the pressure. I'm going to round this to negative 10.6 kilojoules, or you could say negative 10600 joules. If I did not specify which units it had to be in, you could say 10,600 joules or negative 10,600 joules or negative 10.6 joules. And that is PV work.